Alright, the start of the talk is background anyway, so... Alright, I'm going to start. Just fill people in. Yeah, hi, I'm Ambrose. I'm going to talk about local type inference with symbolic closures. Alright, what is local type inference? Well, it's an algorithm that takes in partially annotated programs, sort of like closure programs or racket programs, with some annotations, and then this algorithm outputs an explicit typing discipline like System F. So it uses this local type inference algorithm really comes in three parts. The first is it uses bidirectional type checking. The second is that it infers some parameter types of functions, and the last is that it infers type arguments, which are the arguments to polymorphic types. So I'm going to explain each one of these. So bidirectional type checking is a very simple way of type checking an expression. It has two modes: a synthesis mode, which you can think of as types propagating up the syntax tree, and checking mode, where you can think of types propagating down. So they both have rules. So for example, synthesis mode allows you to, you say that a number can synthesize its type, it knows its type, it's an int. And a string can also synthesize its type, it's a string. And for compound expressions, you can have more interesting combinations of things. So for example, to add one to an expression, this expression synthesizes type int so long as its expression checks as type int. And there's going to be corresponding rules on the right for checking. And one is a simple one that just flips the arrow. This, I'm going to use the mouse instead. So this one here just says that if you can synthesize a type for this, then you can also check it. It's a nice way of combining the two. And down here is the function rule. It says that a function checks of type, is of type T arrow S if we can synthesize the body to be of type S. And notice that this T is explicitly given. And there's actually no corresponding synthesis rule for functions in, for example, System F, which is the target for bidirectional, for local type inference. And here's an example. So an example derivation, type checking increment of 1. We can synthesize this as an int as long as we can check 1 as an int, and then we can use the switching to the other mode, and that trivially synthesizes to int. All right. And this is nice for both implementers and users to conceptualize. It's a simple framework, and it tends to yield predictable local error messages. You can imagine if this wasn't an int, you could blame this particular this expression, and the trade-off there is that a lot more annotations are needed. All right, so one of the other things that local type inference does is infer types for local functions. This is kind of a much more trivial thing, but you notice in System F, the types are attached to the parameter names, but for example, there might be some wrapping of some way that the type actually propagates through the bidirectional type checking. So this int is out here, but it really goes in here, right? So there's a simple way to basically bring this annotation in here. So that's inferring function parameter types, and the other is type argument reconstruction. So we have a polymorphic type here that has, it's the normal, I forgot to put it in, but the normal type for map takes two type variables, and if we add one over this list of strings, then both of the type variables are going to be int. So the local type inference will infer these for you.
What's the distinction between these two scenarios and dictionaries?
This might help. Combining these two doesn't work out very well. So, for example, here we have a polymorphic application on an unannotated function. So we need to infer the type arguments to map and also infer the type of x here. And we basically can't simultaneously infer these with the simple bidirectional formulation of local type inference. And it's for the simple reason that the application rule for polymorphic functions says, okay, it's polymorphic, now all you need to do is synthesize types for the arguments, and now we can constraint solve, the answer. But we've already lost. Like, we can't, there's no synthesis rule for the function. So you're done. So that there's this kind of interplay between type argument synthesis and parameter type synthesis that is called the hard to synthesize arguments problem. And there are varied solutions to this, stopgap solutions in various programming languages. I'm just going to show a couple. And so, for example, in type bracket and type closure, we assume that an unannotated lambda is of type any. This is the top type. And unfortunately, this doesn't check, because over here x is used as an int, and this will throw a type error. And hopefully the user will know, well, it's because type bracket or type closure implicitly put any here. So in TypeScript, it's slightly more interesting, because any unannotated function is given the lowercase any type, which is an unsound dyne type that doesn't do any runtime coercions. So we're basically, anytime you don't annotate a runtime, a function parameter, you're trusting the body of this function and perhaps any consumers of the result of it by introducing this unsound type. And even in more gradually typed like languages like reticulated Python that have real dynamic types, you can see that there's an unnecessary runtime overhead. Like, we can see just by reading this, there's no reason to coerce x to an int here. It's obvious. But the semantics of reticulated Python say unannotated arguments are of type dyne. So amusingly, I am most impressed by Java's solution to this. Because, for example, mapping over a list of 1, 2, 3, like this, automatically infers correctly the type arguments to map and the parameter type for x here. And this is all without any runtime overhead besides the weird runtime overhead that Java lambdas have. You can Google it. It's very odd. I can't say I fully understand why this is, but it seems to work very well. Like, look at this this method chain of higher order functions. Like, all these filters. This is polymorphic. This is a unannotated lambda, and there's a map and there's a for each. So yeah, to me, Java lambdas are the gold standard of what we want to provide our users, the kind of user experience. We can say, oh, don't worry about it, there's no downside, just don't annotate anything. This is what users actually want. They're okay with annotating top-level things, but when they get down to the weeds, you can imagine how many annotations could basically destroy the readability of this code. So the question we're going to try and answer for the rest of this talk is down there. Is this achievable with non-OO idioms or something more like this? All right, so I'm going to use symbolic analysis to try and find a solution to this problem. And we're going to use this running example here. This is a hard to synthesize term because when we use, so it's just a simple let binding of f to the identity function. We call f on an int, we call f on a string, right? But in bidirectional checking, we have to determine the type of f before we get down here. And there's no such thing as unification variables. So this basically, well, this happens to type check with x is n, but let's imagine that it doesn't. Yeah, so the question is, how do we type check this? Yeah. And you can imagine a couple of wishful thinking solutions. The first is we could magically infer some sort of principal type for the function up here, and then just annotate it for all AA, and then it instantiates using the normal type argument inference. And another is inferring a sufficiently capable intersection type for f, to say that Well, to type check this, we know that f needs to have, at least be able to accept an int and a string. And we can also also remember what it actually does. So, for example, this program knows that it returns a string by the fact that it's annotated here. So, just to be clear, this stuff on the left is the input program, the partially annotated, and these are the kinds of system FE outputs that we'd like local type inference to do. And this particular talk, we're going to try and achieve this bottom one within the framework of local type inference with bidirectional checking. All right, so this is kind of an old problem as far as local type inference is concerned. There's a nice paper called "How Good is Local Type Inference" by Hosoya and Pierce, and they basically they say if you want to attempt this problem, there are two main challenges. The first is you want to delay the checking of hard to synthesize terms. So we basically lost the game if we try and type check this before here. Then correspondingly, we need to force the checking of them in places that it needs to be checked to preserve soundness. All right, so here's an example of trying to solve this that doesn't really work. So idea number one, suggestively, is just to inline let-bound functions. So, for example, here we have this f. We're just going to inline the values of f and let local type inference do its magic. And you can see it's pretty easy to figure out what x is. It's just left lambda. So yeah, the answer to how to delay it, well, we just inline the let-bound functions. And, well, how do you force it? Well, it just kind of happens automatically, so you don't need to worry about it. There are several problems here. First is kind of trivial in that if f is recursive, this doesn't terminate. Let's just, that's something that we all have to deal with. But, for example, if f is a more compound expression, it could be quite difficult to tell if it's an unannotated lambda at all. Like, we're going to need more custom rules to figure out whether it's a nested lambda or maybe does it return another lambda. It's like it doesn't quite extend very nicely. And perhaps the most serious problem is that it doesn't bode well with variable capture. So for example, if we have if we say that this function closes over this let, where the y is the result of some crazy side effect, and well, if we want to inline this, well, we can't just inline, this because y, so we need to inline some sort of result of y. So you can imagine doing it kind of like this, and we're now duplicating the side effect, or I could imagine maybe inlining the rights. This doesn't really work, and I could imagine maybe there's some answer to this, but let's just leave it there. This is kind of nasty. It's as nasty as it sounds, inlining left-bound functions. All right, so the second idea is, well, let's just revisit this idea of kind of let polymorphism. And let's just say, well, we can infer a principal type scheme for f and just, make sure each of these f's instantiate to the correct thing. Well, this immediately doesn't work because we can't synthesize a type for functions. We don't have unification variables. So.
Saying that you don't have unification variables. Is this in the context of like a particular framework you're using, or is this some like self-imposed restriction that you have?
Local type inference with like capital LI and LTI. Right. That is a formulation by Pierce and Turner. It's very simple. There is no unification. It's bidirectional, and it does local type argument synthesis, basically.
I think you'd say it's usually used in systems where like Henry Milner wouldn't work. So when there's subtyping or there's other things that start to muck up the algorithm and no longer give you the guarantee that it can reconstruct all the omitted type annotations globally in the program. Okay, that's useful.
Yeah, because this looks really easy, doesn't it? But it's not when you, if this is a Haskell program, it's a lot easier. but if it's like, have predicated polymorphism, subtyping, it's like, oh, yeah. So this is what I'm getting at. Unfortunately, the examples have to be very simple to transfer my knowledge. So I was just saying that we don't have a synthesis rule for unannotated functions. But what would this synthesis rule even look like? Well, let's play with that for a moment. Let's imagine a type that is just kind of an IOU of I will check this function later, right? So let's answer the first question of how to delay something with, well, let's just stuff the entire term, the entire function into a type. Let's say this ampersand, or this and means it's a function. So f is of type its own source code. Let's play with this idea. This is pretty fun. So we have an introduction rule. We now have a synthesis rule for functions. And this is sound so far, because if these invocations weren't there, then we don't need to check that. It's not called. So nothing can go wrong. So we're good so far. So now we have to figure out what are we going to do with the applications. So we need to force these applications with the given argument types. So here we have int as an argument, and you can imagine that checking this function type is going to involve a subtyping check with the fact that it needs to take an int. So you can imagine this int kind of flowing in with this x, and x checking here. And so we now know that this is an int-to-int function by kind of, it's in the subtyping relation. I'll just handle it for now. And similarly with the string, we can say that it's a string, arrow string, because when we symbolically ran it, it returned a string. Okay? But of course, this is a completely undecided and a terrible idea, as is. For example, let's see this auto application. It just calls itself here. So we delay once, and then we check, and then in checking this, we have to check the source code, which in fact also has the same code, and then this will just go on forever. Okay, so let's zoom back out a bit and think about the context of which we're doing this in. So we're in local type inference. We have annotations for top level functions, and in my experience, in a lot of say Lispy languages, is that local functions tend to be pretty simple. They're either impossible to infer or pretty simple. Like they're usually not implicitly or explicitly recursive. Like, for example, that auto application was implicitly recursive, and an explicit recursive would be maybe letrec. And as I just said, we have top-level annotations for our functions. So we kind of have these two worlds. One is super hard. We say, users, please give annotations for these. And this other, we have these local functions that are potentially quite compellingly easy to deal with. You know, if you like we saw like a map of fun, like that we just, that's easy. So this kind of intuition is what we should be grasping at right now. And this, bringing these insights together, it leads to a couple of restrictions. One is that we only delay local functions. If something is a top-level define, we only check it if it has a top-level annotation. Let's say like we were building type bracket or type closure or something, and we're thinking like, how would our users like to interact with this potential unsound, undecidable craziness, right? And we'd also want to not allow a delayed function type to escape into another top-level form. So we at least have the symbolic analysis happening in one top-level form. And let's just assume that we're not interested in these impossible cases, recursive cases, and just use fuel and just say we can only symbolically reduce something a certain amount of times. And say if it's 50 times, let's just assume that it's going to diverge, and let's just throw it away. But you can imagine that simple local functions probably don't take a lot of symbolic reduction to make this happen. So for example, if we go back to our auto application, if we give some fuel, we can see that we hit a reduction limit after a certain number of symbolic reductions, and we give a type error to the user and say, hey, this needs annotation right here. We can't symbolically reduce this. But notice that we've basically been symbolically running this function. So we have some information about what f actually is, and we can provide that to the user. So it's a sort of semi-automated annotation tool, like a coach. Say, hey, maybe you want something with one argument that kind of takes a function-ish thing. You know, of course, this is like a recursive type, and it's kind of weird, but you can imagine at least an 80% case. Yeah, okay. And of course, the trade-off is platform dependencies. Whenever you add fuel, you know, you have two different versions, you change the fuel, you release one with more fuel, and now your program doesn't type check. So I'm imagining you would give enough fuel for most non-recursive functions to type check maybe 100 or 200, and then you would reset it for every top-level function. So that's kind of what I'm thinking about. All right, but we already have a function. We already have a problem. That's variable capture yet again. So you can see here we have y, let's say it's just 1, is captured here. If we give this a symbolic, a delayed function type, then by the time we get down here, we're going to have the type check y, but we don't know the type of y. So let's generalize this idea of a delayed function type and put a type environment. Pair this code with a type environment. So this is what I'm dubbing a symbolic closure, because calling it a typed closure would be way too confusing. But it is in the same way that a runtime closure pairs a runtime environment with some code, a symbolic closure pairs a type environment with some code. So now you can see if we need to type check y, we can just look at the environment in which it was checked in, or it was found in, which is here, where y was int, and now we can check y. So, yeah.
So you put y in type who's there, despite the fact that it doesn't appear on the source code. Does this suggest that there needs to be some checking step before you construct?
Yeah, so this is where the bidirectional checking forces you to do this outside-in checking. So by the time you're here, you would have noticed that your scope includes y being 1, right? And when you introduce a symbolic closure, you just like a runtime closure, you just grab whatever is in scope for later, put it in your pocket. So this is just whatever you need, whatever's in scope at the time that you get to this, that you check this function, you also carry it along for when you need to check its body.
So for whatever reason, you couldn't infer the type of y without necessarily being there?
Yes.
At using the rest of the program?
Yeah. You need to. If one was not checkable, this would yield a type error. Yeah.
Maybe a corner case, but say the function has a type error in it that never gets used. Does this algorithm mean that you never actually get checked, but it's like considered dead code and you don't check it?
The tree falls in the woods.
Okay, fair enough.
Sound. I consider it a feature.
Just wondering.
Yeah.
You get symbolic closures in your environment that then get updated as you
Yes.
do the
So,
normal
linking it with Ryan's question, if y used a symbolic closure, you'd now have a symbolic closure inside your type environment that you're paired with another symbolic closure. And now, just to zoom back into the overall problem, we're trying to translate from partially annotated programs to System F. System F does not have symbolic closures, so we're going to have symbolic closures everywhere, potentially, but we're going to have to compile them away somehow into a function type. And I'm going to try and convince you that I've got a fairly good algorithm. Right now, here's an example elaboration. Okay, so these should be familiar. This is F. It's an identity function. We call it twice with different arguments. And what we want as the output, so local type inference will infer this, which is this is very easy to check. It's the identity function that can take either an int or a string, and when it's an int, it returns an int. String returns a string. Okay, so
I understand the intersection.
yeah, it's an ordered intersection type.
It does not stay for identity.
Correct. Yeah. Yes, this is an intersection type. This is an intersection of arities, capabilities for this function. Okay, so first of all, first order of business is to not check F. Really, don't check it. And notice that we don't have anything in scope, so it's just the empty type environment. So F is of type symbolic closure. Second order of business is to check, well, now that our function can actually be run, we need to exercise symbolically this function. And this basically manifests in a sort of subtype test that F, which I'm just going to abbreviate as F here, substitute this in this symbolic closure, is of subtype int array something. And we know it returns int here, so we learn that it's int array int. Similarly, with the next call, we learn that in trying to feed in string, we get out a string. And finally, we replace F's type with its capabilities. And we kind of do this recursively. For example, if F's type has a closure in it, then we would, a symbolic closure, we would also replace it with its capabilities. And this can end up with infinite types, which is why this elaboration here needs recursive types. So, yeah, any questions about this elaboration?
Could you repeat that sentence just one more time? This elaboration here could end up with recursive types.
Yeah, it's very subtle.
Is that for the applied?
Yeah, that's a good example. So in F applies F, maybe I'll just go back to it. I don't know where it is. Okay, so you can see F is being applied to itself. So this F is going to receive its own source code, its own symbolic closure, and it's going to receive it over and over and over. So there's a loop, there's a knot that needs to be tied here. And recursive types allow us to do that. So,
Earlier in the talk, you suggested that this might actually be rejected for not having enough rule, but you're saying you actually could have this.
I'm saying that, say, no, I'm not saying we could type check this because this
Or
would.
rather, if you were to write this up in system F, would have root? I'm not sure where exactly it is.
Yeah, so this example is just a very simple example to say that this takes as long as beta reduction. So if the fuel gives you enough fuel to beta reduce enough times, then you can give you can type check something with a correct elaborated type. But you
not
can't.
necessarily
Yeah.
this example.
Yes.
Example of sort of
Oh, yeah, exactly. That maybe call themselves once and then throw themselves away or something like that. Yeah. Yeah. Any other questions about this? Okay. I'm just going to throw out a couple more tidbits about symbolic closures. Talk's basically over. That was the meat of it. So we can just look at some pretty pictures for now that look like that. So this is the typing rule for applying a symbolic closure. So F applied to E. If F is of type symbolic closure, notice that we have this gamma prime is distinct. So this is the type environment of which F was defined in. And here's the source code of F. And E is of type sigma. Then if we extend using the this type environment over here to to check the body, this body over here. If this is of type tau, then that's what the result is. I just butchered that. Please, yeah.
So I understand this rule.
Yep.
What I don't understand is how you get from having F as a type symbolic closure to massaging that out into an actual type that you can embed in the system or whatever.
This was this example here. So the intuition is when we saw it symbolically reduced as an int to int. Well, let's just remember that. We saw it as a string to string. Well, let's just, find all the usages of F that is embedded in our types and just replace it with all the capabilities we needed to do. And then, yeah.
Do you encode that as a typing rule though somewhere? Or
that's like post-processing. Like you let the local type inference go and then you process out your arrays. Yeah.
So, how disappointing you have some
Yes. That's an excellent question. I think we were on basically that slide. There is a corresponding rule in the subtyping relation that basically does the same thing. It says that if you can check a symbolic closure as a tau to sigma if you can check the body as returning sigma if you assume if it takes a tau. And you will notice that subtyping relation will call the type checker. And via subsumption, actually, this is where the infinite loop comes in, because now we have these symbolic things hanging around in our types. We now have a subsumption rule that allows us to call the type checker again. This is where the infinite undecidability comes from, the infinite loops. And yeah, the fuel allows us to cut this short when we might. Assuming we have a good fuel that might be generally useful. Any follow-up questions to that?
What are the different turnstiles on this slide? This turnstile and turnstile superscripts.
I apologize for those.
Were those already mentioned?
It was because I copied this out of my in-progress paper.
Okay.
They are basically the same thing.
Was it check and sync at one point?
This one's colored actually.
Or? Okay.
Colored local type inference.
Okay.
Yes. Yeah, all those colors I showed you at the beginning, like this would be colored in red, this would be colored in blue. I basically compiled my paper that deleted all the colors, and this is what you're seeing.
At the beginning you mentioned Java being able to do a decent job of this sort of problem. I didn't catch why it would solve this problem. Did you?
I have no idea.
Okay. Is what
I honestly have no idea.
Yeah. Is what they do documented in any to your knowledge?
No. I see claims that it is sound somewhere in Java spec somewhere, and I don't see any. Like, it looks like a pretty hard problem, but I don't see any evidence that a principled solution. I would love to see it. Yeah. Andre?
So, kind of in that direction, like, have you considered some sort of, so this kind of actually reminds me of what Lee is doing, where they actually wrote their entire type checker in a coroutine runtime, so that they can, like, when they get to something that they can't check yet, they just like put it on a waiting queue basically until everything, like you give up the type check and once everything's on the waiting queue basically. And then, yeah. But you're continuously like looking to see, can I type check this thing? Can I type check this thing? Can I type check this thing? And once everything can't be type checked, and you're like, okay, here's the program back, I couldn't do it.
Yeah, the one thing I like about symbolic closures is that you just introduce a type. Like anyone in this room could implement it. If I say, I challenge you to put the functions type in a function's code in its type, and you would figure out, well, you need its definition type environment, so I'm going to put that in. Well, I guess it's undecidable, so it's the fuel, but it's very clean extension of local type inference, which makes me think someone else has invented it, but here I am talking about it. Okay. So this has really interesting implications with polymorphic type checking. And I don't know if anyone noticed, but I didn't actually show how to solve the hard to synthesize arguments problem, where you have to synthesize both the arguments to map the type arguments and X here. But I have a model that kind of seems to work, but I don't know really why it works. I'll give you some intuition as to why we can check something like this. So we're going to have an application rule that notices that this is a polymorphic function, and then we're going to type check the arguments, and then we're going to do a constraint resolution. But first we're going to look at the type of map. We're going to look at the type variables in map and look at their variance and look at their position relative to arrows, and then derive a data flow graph from the type. So if you think about how map works, you can imagine 1 flows into here, and then ink flows out. And then 2 flows into here, and then ink 2 flows out, and then like that. And you can see that in the type here. I still don't quite know what the arrows mean, but I think it's... so this is in a contravariant position, and this is in a covariant position. So there's some, unfortunately, this is just going to be a stream of consciousness. But you can see that what I've just outlined here, you can see in the type here. You can also see that there's no loop. Like, for example, if A was on the right here, A could be fed back into itself. But all that can happen with B is that it gets spat out. For example, like fold. Fold has that sort of loop, or like the identity function. The identity function doesn't, in type closure, it could call itself many times because it has an alpha. It could just, there's no reason why it couldn't. But here you can see that it's impossible for B to be fed back into the function, which means that if this function is a symbolic closure, it's only going to be called once per collection. But that's assuming this is heterogeneous. If this is homogeneous, then it's only going to be called once. Okay, so
you said B couldn't be fed back in. I would imagine that would be the case in a language where polymorphism is treated very, sacrosanct, and where you can't have subtyping with type variables, but in type closure you can't you? Can you ask what the B is, discover it's an A, or I guess you wouldn't know, would you?
Can't cast something to another type variable
right.
without an unsafe cast,
okay.
Which then you're on your own.
You could figure out if it was like an int and pass it to a function that expected ints, but since we don't know what alpha is.
Yes.
Anyway.
Yeah. No, it's a good thought experiment. Like, if you really wanted to, how could you make
But there
this?
may be some B's that you could pass in, but you couldn't do it.
The implementation of the map wouldn't type check if you tried, because it needs to work for all B's. And there's no bound on A to say how it relates to B, so they're completely distinct. As I said, this sort of data flow diagram I'm still not 100% sure about. There's strongly related work is in ML. Is it ML sub? They compile polymorphic types into data flow diagrams like this. And just to give a kind of a gist of the mechanism that you might use to type check this, you basically generate a couple of constraints. First is which this A to B has to be a super type of the symbolic closure, and that this sequel of A is a supertype of the vector of numbers. And basically, because A's lower bound here is going to be bottom, we can just assume that A is bottom on the first time around. We can basically feed in bottom to type check X here, and then get out B as an int. So it doesn't matter which order. So notice that it'd be great if we could type check this argument before this argument, because this one tells us that it's a number, like easily, but that's not how it works. So as I'm alluding to here, there's an iteration between, we might have to call this symbolic closure multiple times and gather more information. So in the first pass round, we might know nothing about A, but then we learn that A is a number from the second constraint, so we have to go back to the first constraint and symbolically reduce this function with an int, and then B and A are probably going to stabilize, and then we can give it the instantiations. That's the hand wavy. And yeah, future work is what if this data flow is recursive. A couple of related works. This is, it's kind of hard to find related works to this because it's such a goofy, it seems like one of those ideas that someone probably thought about in the 60s and said, this is stupid, and then no one published anything on it. But there is a long series of literature on intersection type inference, and there's this idea called an expansion variable, and it's basically a placeholder to be able to make your type larger. And if you imagine, remember that our goal was to create a large intersection type for this function. You kind of imagine that there's like a placeholder that lets you slot in more and more types. You can kind of see this in this, this very vague but hopefully evocative diagram that shows that they take a type that is somehow, that needs expanding, and then they copy it into two places. And you can imagine maybe the ints are over here and the strings are over here. And this has a similar cost. Its inference cost is equal to the cost of data reduction. But yeah, I'm only vaguely familiar with this. Next step is to learn more about it. And the other end of the spectrum is just trivial, not trivial, but like straightforward extensions to local type inference. So for example, here we have a function g that takes in a function that we know is an int. Well, it seems pretty obvious that we know that this int should annotate this x. So in other words, colored local type inference allows us to propagate partial information. We don't know what the return is, but we know that the input is of this particular type. And this turns out to be very useful in Scala and anything that you need to call a method on.
It's sort of like a weaker form of unification in some sense.
It's the way that I think about it is that remember the colors, the synthesis and checking colors. It allows us to propagate. It allows us to be in checking mode in bidirectional checking, but allow part of the type that we're checking to be synthesized. So this int will be checked. This A will be synthesized, and then once it bubbles back up, we can use it to solve the rest of the program. So. Yeah, so some, hopefully a nice summary. The big picture is we have local type inference, and it requires annotations. And unfortunately, local type annotations are super annoying. We don't want our users to have to bear them. We've got a couple of insights. One is that, well, we have lots of annotations for top level things, and local functions are kind of trivial. So we can bring all these together and use a symbolic analysis to infer simple local functions that I like to think of as local type inferences equivalent to crush. It's like a little, okay, crush this. And you know, if you fail, well, I should have known better, that kind of thing. All right, thanks. It's the last part of my thesis, so I'm still writing. But no.
How do you know how much more complete, or like, can you give an example of something that this can check that colored local type inference can't?
Well, let's have a look at it in my model. Let's see, we'll look at the unit tests to remind myself because I've been writing. So there are these ridiculous stress tests of left polymorphism that basically show the exponential or double exponential, in some cases, behavior of left polymorphism. And in understanding them, I've tried to embed a lot of them in my using symbolic closures. And so, for example, this benchmark here, let's find a smaller n for the benchmark. Oh, whatever, this will do. So it's basically a lambda encoding of pegs. So, but there's no annotations at all. If you just ran this program, I think it returns a function. Well, look, it returns a function that returns, that takes int int. But, I mean, it's kind of, this is a really unfair comparison. Like, immediately, look, x, look at how many functions we need to, like, P1, it's used twice over here, and, P2, like, this is the kind of thing that looks easy and you just wish that there was a crush for, and you don't care what x is supposed to be here. I don't know if I have. I just started elaborating these programs, so let's have a look at the kinds of types that we get out. So, oh, and the other cool thing is that using this, we can expand out lets into their lambda representation because they would only be called once. Normally that doesn't work with local type inference because left lambdas they involve unannotated functions. But using this, you can just use the left lambda, you can just infer the lambda as a symbolic closure. Like, for example, here, this let A1 here becomes a function that takes in an A and returns an A and then gets applied to 1. But you can see that there's an annotation here that tells our dumb type checker what the annotation is here. So, yeah, there's some recent work that called let arguments go first. And it was basically arguing that if you type check arguments first and then type check functions second, you can get this kind of embedding of you can expand lets into lambdas. But this is just doing straightforward left to right predictable type checking and still gets the same result. So yeah.
Is benchmarks we just dedicated to figuring out programs that will or will not type check in our system, or is it also to gauge how quickly it infers types?
To gauge how quickly they infer types, how large the types are, it turns out if you try and print, so in some of these pathological left polymorphic benchmarks, a lot of the overhead is actually printing the type. And sometimes it's, can't say I fully understand why, but it's doubly exponential to print the type. And if you compile the type into a graph and reused names, it could be singly exponential. And there's like an interesting correspondence between how you print out a symbolic closure with this sort of singly exponential printing out. And yeah, that was kind of vague. I was going to say something else.
You just have a lot of difficulties. Does this tend to perform well on most of these programs?
So,
doing type of programs you try to allow with this particular product?
well, part of why I'm so excited about this is because it seems to be almost infallible, like this model. And I know that it's unsound in some ways because I've been kind of like, oh, maybe I can do it here as well and here as well. But like, I've been super impressed by how much like crush this is. And I'm just waiting for the other shoe to drop. Maybe this is unsound. Maybe there are some pathological cases that are common, other than infinite loops in your programs. But the more I try it, the more robust it seems. So yeah, I'll definitely let you guys know when I break it. But I'm trying.
With random generation of terms to express
Oh, this is much more efficient. It's crazy, some of the left polymorphic. There are different, like, if you think about it, the best benchmarks are the ones that reduce the most. Right? And left polymorphic, it doesn't matter how many times it beta reduces, because that's not what left polymorphism does. Left polymorphism blows up exponentially because of things like generating an exponential number of type variables, or copying an exponential number of function types, that kind of thing. And then having to print all that stuff out. But that's not what's happening with symbolic closures. There's actually some beta reduction going on. So it was interesting to see that symbolic closures are much better at these benchmarks once you elaborate out the actual types. But yeah, I'm imagining there are different kinds of benchmarks that I haven't quite got to that. But yeah, it's all kind of part of the hypothesis that maybe these benchmarks that are pathological are pathological. Like they're like part of this work as well. If local functions are generated pretty easily, like let's see. Well, the part I'm most scared about is like checking something like fold or reduce, where you have this loop in the polymorphic type inference that you try and get to a fixed point, which makes you keep reducing things, and actually haven't nailed that out, so there isn't really much empirical evidence one way or